best student paper nominee. So it will be Alexander, and room is yours.
Okay. Thank you. Good morning, everyone. My name is Alex Scarlatos. I'm a PhD student at UMass Amherst, and I'm going to be talking about a method for generating feedback with large language models using a reinforcement learning approach. My co-authors are Diggory Smith and Simon Woodhead from the AIED Learning Platform, and my advisor, Andrew Lan. So this might be an obvious question for everyone here, but why do we even want to use LLMs to generate feedback? So we know that feedback can help students understand their mistakes, which is really important, especially in math, which we're studying. A student makes an error, they need to know what they did wrong and why it's wrong, and maybe get nudged in the right direction to understand the correct solution. And there's a lot of research out there showing that feedback does improve student learning outcomes directly. This is just a couple examples here, but there's a lot of research on this. And finally, we can reduce teacher workload by automatically deploying feedback. We obviously want teachers to be less stressed and to have more time to focus on more important things like meaningful student interactions other than things that can be automated. But generating feedback with LLMs is not easy, as we all know, but I'm gonna give a motivating example here. So let's say we have this relatively simple question, what is the square root of 9, where the correct answer is 3, but the student gives an incorrect answer of 4.5. So we all know what went wrong here, and here's a feedback that a human wrote. I think you've halved 9 rather than square rooted. What number when multiplied by itself will give us 9? This is a really good feedback because it points out what the student did wrong, so they know, that they actually divided by 2. That's not the same thing as square rooting. And the teacher tries to give the student a hint so that they know how to go about solving this problem. So let's look at a feedback that was written by ChatGPT. The square root of 9 is not 4.5. Remember, the square root of this number that when multiplied by itself gives the original number. So this feedback is still correct, which is great, but it's not quite as good because it doesn't point out that the student did 9 divided by 2 rather than the square root. So it's a little bit difficult to say automatically which feedback is better, but I think we can all agree that the human feedback is slightly better in this case. And then let's look at one more feedback, and this is a feedback that's generated by Codex. If you guys can't see, I'll read it out loud. The square root of 9 is 3. You might have been thinking of the square root of 81, which is 9. So this is just a hallucination. The student was not thinking of the square root of 81. Their answer was 4.5. It's not mentioned here at all. So this feedback is just wrong, and we have to be able to generate feedback that's correct, but that also is high quality. So this is a double challenge. So what are these challenges? Let's formalize this. So the feedback generation system needs to understand the solution to the problem, and it also needs to understand what the student did wrong, if they had a misconception or what kind of error that they made. And then we also care about educational goals and pursuing them with the feedback. Like, we want to promote a growth mindset, we want to encourage the student and help them solve the problem on their own and not just give the answer away directly. There's also challenges with evaluating feedback. We have to account for the correctness of the feedback, but we also have to account for the alignment with educational goals, and this can be quite challenging to do automatically. So text similarity metrics are insufficient, they're unreliable. You can have feedback that is very different from the ground truth feedback, but it's very good, but you can also have feedback that's similar to the ground truth feedback that is really bad because something could be subtle but wrong with it. So what people do to account for this is they design rubrics where there are different criteria that the feedback is supposed to meet, and teachers evaluate the generated feedback. This is very reliable, but it's very time-consuming and expensive, and especially if you want to use this evaluation in a training loop, this becomes even harder, similar to like what OpenAI does when they're training their RLHF models. So all of this leads to the key insight for our work, that if we want to generate good feedback, we actually need to be able to understand what good feedback is and assess this automatically. But if we can automatically evaluate the quality of feedback, then we can define a goal-oriented training objective, where we give a reward for the feedback getting a higher score with the evaluation system. So this leads naturally to a reinforcement learning setup, where we have a reward for the quality of the feedback, and the policy is the feedback generation model. So I'm going to talk specifically about how we approach this framework. So in the first step, we're going to overgenerate a very large set of feedback using large language models, specifically Codex and GPT 3.5 Turbo. So these are older OpenAI models. And we go from a small set of teacher-written feedback to a very large set of mixed teacher and language model written feedback. Then we're going to take all the feedback that we have, and we're going to evaluate it automatically with GPT-4 using a rubric that we designed. And then we can give a score, a numerical score to every feedback. And then the final step is we're going to use direct preference optimization to train a local generation model. So with direct preference optimization, you have to pick pairs of feedback that are better and worse. So we can use the assigned scores from the evaluation system to say what's a better feedback and what's a worse feedback. And then we also do an additional technique where we use mismatched pairs from the data to form additional pairs. So I'll talk about all this more later. And an alternative to DPO is we can train a reward model on this over-generated feedback and then use PPO, which is similar to how ChatGPT was originally trained. But this is a more complicated approach, and PPO and DPO have the same final objective, so we opt for DPO in this work, which is simpler. So let's talk about the first step where we're over-generating feedback. So we have a data set of multiple choice questions in math. So there's 3 incorrect questions for 3 incorrect answers given for every question and a teacher-written feedback for each. So we feed an incorrect answer to a language model and it generates a candidate feedback. And our goal here is to generate a diversity of feedback where some feedbacks are high quality and some feedbacks are low quality, because for the reinforcement learning algorithm to learn, it has to know what good and bad examples are. It has to have both high and low rewards assigned. So we use a variety of prompting techniques, such as different techniques for selecting few-shot examples, such as random or using text similarity. And then we also do zero-shot prompting with a different model. And we find that this gives us a good variety of feedback that's correct, incorrect, and both aligned and unaligned with educational goals. So we kind of hit all of the full spectrum here. So the second step is to take all of our feedback, both the teacher-written and the automatically generated feedback, and evaluate it with GPT-4. We use zero-shot chain of thought prompting here, where it's given the rubric and it outputs a final score. So I'm going to talk about the rubric that we designed. So the first item is that the feedback must be correct, so it has to be relevant, and it can't make any incorrect statements. The feedback should not reveal the answer to the question because we want to encourage the student to solve it themselves, but it should give a suggestion for helping the student get towards the correct answer. It should also point out the error that the student made directly, and finally, it should be positive and encouraging in tone. Then we assign a final score, which is the average of these 5 binary labels with a slight adjustment, where if the feedback is incorrect, we automatically give a score of 0, because we don't want to give any reward to an incorrect feedback. So if it's incorrect, it'll have a score of 0, otherwise it'll be a score ranging all the way up to a value of 1. So finally, we have to train our generative feedback model now that we have our generated feedback and our scores. So we assign pairs of feedbacks, and then we train with direct preference optimization. So I'm going to talk about DPO and how we assign these pairs next. So a review of DPO, probably a lot of people don't really know this algorithm that well. So this is an offline reinforcement learning algorithm. So you're given a data set where you have a bunch of inputs and alternative outputs for that input. And the labels in the data set say which outputs are better than the other ones. So you have these pairs. So in our case, we have a question and incorrect answer, and then 2 feedbacks. And we say, this feedback is good and the other feedback is bad. And the algorithm makes it so that the good feedback gets more likely and the bad feedback gets less likely from the generative model. This is DPO. So the key with DPO is how do you construct your pairs? So we have all these feedbacks that we generated with LLMs, and we have the scores that were assigned by GPT-4. So we're going to look at every possible pair of feedbacks for a question and incorrect answer, and we're going to just use the scores to say which feedback is better and which feedback is worse. So we have the scores 1, 1, 0.6, and 0.2 for these 4 feedbacks. We're going to look at all the pairs. So feedback 1 and 2 have the same score, so we're going to ignore this pair, but then feedback 1 is better than feedback 3, and it's better than feedback 4. So we're going to construct 2 pairs there where feedback 1 is preferred and the others are unpreferred. And then we do the same for the rest of the feedback. So we get up to 6 pairs for every question and incorrect answer. The next method is using mismatching from the data. So we have this nice multiple choice question data set, and we have feedback and incorrect answers all paired up for every question. So we're going to take the current incorrect answer and the corresponding feedback and prefer that feedback to the feedback written for a different answer. This is a little confusing, so I'm going to give an example. So we have this, what is the square root of 9, and the answer is 4.5, and the teacher written feedback says, I think you have 9, blah, blah, blah. So we have another answer for this question, 81. And the teacher written feedback for this says, I think you have squared 9. So there's a very subtle difference between these 2 feedbacks. I think you have 9, and I think you have squared 9. And this is what we would call a hard negative in machine learning. And this has been proven to be very effective for training models, where there's a very, very subtle difference. It's right on the edge, and it forces the model to focus on the things that are important. And here the thing that's important is the difference between halved and squared. And we find that this method really increases correctness in our model. So I'm going to talk about our experimental setup. we have a data set of about 1,400 middle school level math multiple choice questions from the AIED system. And the methods for feedback generation are zero-shot prompting, Llama 2 chat, the 7 billion parameter version. Supervised fine-tuning that model, just using the teacher-written feedback, which, again, is a small data set because we only have 1,400 questions. Then we do our DPO method, where we only look at the score-based preferences. And then we'll do DPO, where we have the score-based preferences and the mismatch-based preferences. And finally, we do zero-shot prompting with GPT-4. So for all of these methods, we include the feedback evaluation rubric in the prompt so that the methods know what criteria they're being evaluated on for fairness. And in the end, all of the results are going to be evaluated by GPT-4 using the rubric, and I'm going to justify this choice later. So let's look at the results. So we have the Llama results in the second half of the table, and we have all of the labels and the aggregated score on the right, and then we have some reference-based metrics on the far right. So if you look at the zero-shot and SFT methods, they actually achieve the same score of 0.49, which is interesting, but they're better at different aspects of the rubric. Zero-shot is very positive, whereas SFT is not, but SFT is less likely to reveal the answer. So we see that zero-shot is actually not that great at following instructions for the Llama model. Both of these also have pretty low correctness. So then when we train on DPO score, we see a slight improvement in correctness, but we see a huge improvement in a lot of the educational like the pedagogical labels. So suggestion goes up a lot and diagnostic goes up a lot. So we're getting much more aligned when we're doing DPO. And then finally, when we include these mismatch-based preferences, then we get a huge boost in correctness, and this is what brings the score to the highest level here. So we find that this is actually a pretty critical technique. If we look at the human-based, the human-written feedback, we find the final score is pretty similar to our method, but this is a little bit of an unfair comparison since the teachers were not looking at this rubric, the rubric when they were writing the feedback. They were kind of just writing whatever feedback they thought was good, so this is not the best comparison, but it is interesting to see that the final scores are similar. And finally, GPT-4 gives its own feedback very, very good scores, almost perfect scores, and this is almost certainly inflated because there is a bias for the evaluation model towards the generative model. And I'd also like to point out that all of the Llama results are also slightly higher than they should be, but I think that the relative ordering is still correct. So I'll talk about this evaluation in a bit. But I just wanted to give one qualitative example. So we have this question, what is the highest common factor of 8 and 24, where the correct answer is 8, but the student gives an answer of 4. So the human says, you've given a common factor but not the highest, which is correct, but they don't give a hint. So this isn't the best. And then GPT-4, I'm not going to read the whole thing, but it ends up giving a hint, but doesn't point out the incorrect answer, which is interesting because it's actually been prompted to do so. It kind of ignores the prompt. But then for our best method with the score and mismatch preferences, it both points out the error and gives a suggestion, and it's correct. So we actually get the most aligned feedback, and it's correct with our method here. But for the rest of the Llama-based methods, they actually hallucinate and give completely incorrect feedback, not understanding that 4 is a common factor of 8 and 24. So we evaluate our results with GPT-4, so we have to ask, is it actually a good evaluator? So what we do is we have humans annotate 80 randomly selected feedbacks using the rubric. We get an average across label Cohen's kappa of 0.43, which is kind of low, but it is a very challenging task for humans as well as models. And also some of the labels are somewhat subjective, so this brings the score down a bit. But then we compare GPT-4's annotations on this set with the human annotations, and we get pretty good accuracy, 0.76 accuracy and 0.71 F1. Again, these are brought down a bit by the subjective labels, but there are a couple issues, and we find that the biggest issue is that GPT-4 does hallucinate when evaluating feedback. It often claims that the feedback addresses a student error when it doesn't actually address the error. It just comes up with something that the feedback said that it didn't actually say. So this is kind of a big issue. And I'm just going to give one example of this. So the question is, a jacket is reduced by 20% on a sale, and then there's a loyalty card for an additional 10%. What's the total percent reduction? The correct answer is 28%, and the incorrect answer given is 8. So this incorrect feedback says, I think you've added the two discounts together, we need to use multiplication. The student clearly didn't add 20 and 10 to get 8. This is not what happened. But GPT-4 says, the feedback does not make any incorrect statements. It correctly identifies the student's mistake of adding the discounts together instead of multiplying them. So the issue here is that GPT-4 is not doing the required numerical reasoning to validate this. It thinks that the student added 20 and 10 to get 8 because it's just not thinking about it. It's not doing the mental math. So this is a good example of where it still struggles. So in conclusion, we find that our approach is very good for improving correctness and alignment with educational goals, particularly on local models. So to prefer supervised fine-tuning on a very small set, you can use this DPO approach with labeling from GPT-4 to get much better results. But some issues are that LLMs are still making factual errors, and there are problems with both the Llama models and with GPT-4. And then when we use GPT-4 as an evaluator, it's still making logical errors sometimes, it's still hallucinating sometimes, so we need to address these issues. So the first thing for future work is addressing these factuality issues, and one thing that we've thought about is using different prompting techniques, such as self-reflection, which is an advanced prompting technique, and you can also use random sampling and then taking the majority vote. So we also want to include humans in the RL training loop, which could help improve the feedback evaluation, and we want to apply to other domains such as language learning, which I think would be an interesting application. So thank you, everyone. This is a joint effort between UMass and AIED, and here's the QR code for the paper and the code. It's at the bottom.
Yeah. Yes, so any questions? Yes.
You said something about model being biased when it is evaluating other models' work versus humans' work. Can you expand a little bit about that? It's really interesting.
Yeah, so we find that GPT-4 often thinks that the feedback that it generates is correct no matter what, and here's some intuition behind it. GPT-4 generates this feedback, so it thinks that what's generating is correct. So then when it's asked, is this feedback correct, it already has this initial bias of assuming that the feedback it was generating was correct. So GPT-4 is generally biased towards thinking that incorrect feedback is correct for this reason.
So when you ask follow-up about the feedback, does it have the knowledge that it was generated by GPT in context? Meaning, have you done like a context reset and said, here is a feedback generated by someone, can you evaluate that?
Yes, all of our evaluations are completely context-free to reduce bias. So yeah, it doesn't know what method was generating the feedback.
Cool, thanks for the great talk. I had a question about whether you've tried filtering out the data where the model either hallucinated or provided poor feedback, because I'm wondering like how good could you do just on like clean quality data, right? Like I could be training on less data, but like really high quality, rather than like a lot of data and like mixed quality.
Yeah, this is a great question. So I think that there are kind of two different paradigms. So DPO requires you to have negative examples as well as positive examples, but people have done similar work where they generate a bunch and then they only keep the high quality ones. So this is just a different approach. We decided to go with this because DPO is very popular and successful right now, but I think it'd be interesting to look at this one as well and to compare results.
Yeah, thanks for the talk and really cool approach. I was wondering, because it sounds like this is a lot of work to make this all, create all of this stuff. Do you have some sense of how generalizable this is to other applications? Because of course, this I would imagine is most useful if you can do this once and then apply it in a bunch of different settings.
Yeah, that's a really good question. We actually have another paper from our lab where we do this with Socratic question generation, and it's a slightly different approach there where we ask GPT-4 to generate questions that are bad intentionally, and then we pair these with the teacher-written questions, and we find a performance improvement by having these negative examples. So I think that this general approach of over-generating, evaluating, and then using DPO is quite generalizable across domains.
Yeah, hi. Thank you so much for the wonderful talk. The method looks great. The numbers look fantastic. However, I'm wondering about like more qualitative issues, like what kind of pedagogical design principles did you use for evaluating feedback, you know, like good or bad? I'm referring specifically to slide 16. You said it was the example with the highest common factor of 8 and 24, and the teacher said, you have given a common factor but not the highest, and you said that's not good feedback because the teacher did not provide a hint. Actually, the teacher did provide a hint. He said, he or she, they said, not the highest, and I would argue this is a hint. So I'm wondering, you know, about the design principles behind putting together feedback.
Very brief answer.
Oh.
Very brief.
Oh, sorry. Yeah, this is a really good point, and I think this also points out, I mean, I didn't really consider that before, but I think it goes to show that the rubric items are a bit subjective. And yes, it is kind of hard to evaluate the pedagogical principles. Our rubric was designed inspired by prior works that have very similar rubrics, but we didn't consult teachers for this, and obviously you can see from the results that the human written feedback doesn't always score the highest on the rubric. So I think there is a little bit of a misalignment, and I would say that this is maybe just going in the right direction, but probably we would want to refine the rubric, refine the evaluation scheme for future works to be more aligned, and be, yeah, especially with what teachers think is good feedback. It's a good question.